X-ray background. Then he moved to something more with more physics in it. So he's an expert on compact objects at all mass scales, so say binaries, supermassive black holes. He also worked on supernovae and neutron stars, I believe.
A little bit.
A little bit. So his primary expertise is on high energy astrophysics, but not only that. I mean, he's using multi-band data as normally people do these days, and also formerly. And so, as I said, he worked all around the world. After Cambridge, he's a fellow in Chile. Then he spent, I think, 6 years in Japan, and then he went back to UK. So today, he's telling us about formation and demographics of black holes in the Milky Way. Then I think at the end of the seminar, he will present us some nice idea about future prospects for space-based missions to detect funny things. And Poshak is staying, he joined us on Tuesday and will stay until Friday, until tomorrow. So he's in the guest room on the 3rd floor if you want to talk to him. Maybe not tomorrow afternoon, perhaps he wants to do some sightseeing, maybe. But anyway, if you want to talk to him, he's on the 3rd floor in the guest room. So 45 minutes, I'll give you 5 before the end. Okay, please.
Okay, thank you very much, Roberto. It's my 3rd time in Bologna, and every time I come, I love it even more. So thanks for having me. And yeah, I'll be talking today about black holes in the Milky Way, stellar mass black holes. But don't worry, I know a lot of you work on AGN as well. It's my first love as well. I will talk about AGN towards the end as well. So yeah, I'd like to thank many of my collaborators. In particular, some of the work that I'll be presenting has been carried out by my postdoc, Corey, UA, and my student, Cordelia as well. So if you want to study black holes and neutron stars, it's actually, nowadays, it's quite easy. All you do is you take an X-ray telescope, point it at the sky, and the vast majority of sources that you'll detect will be black holes or neutron stars that are growing, accreting matter. So this is a picture from the MAXI Japanese all-sky camera on the International Space Station. And almost every single object that you see here, almost, they are black holes or neutron stars in the Milky Way, accreting matter. That's the plane of the Milky Way you can see there, and lots of sources all around. And then in the background, you can also start to see some faint extragalactic sources now starting to pop out. The different colors just tell you about different temperatures of hot gas accreting onto these compact objects in most cases. So don't worry about that detail. So how many such objects are there? We ask ourselves, how many black holes should there be in the Milky Way? There are many estimates for this, but just as order of magnitude, if most massive stars collapse to form compact objects, which is, order of magnitude reasonable assumption, then perhaps there'll be about 1% of stars becoming black holes or neutron stars at the end of their life. So if there's 400 billion stars in the Milky Way, then we should expect something like 1 billion compact objects. That's a lot. Okay. At the moment, we only know of one isolated stellar mass black hole, pretty robust, probably. It's the only one that's believed, at least. There's many isolated neutron stars that are known, for example, in pulsars. These were probably also formed in binaries, and then, as I'll discuss, something happened to change their life, and they became isolated. There will probably be many objects that should be found in binary systems, but the estimates here are very uncertain. Depending upon which paper you read, you might expect something like 1,000 to 100 million. Okay. So somewhere in that range, we expect compact objects in binary systems right now. And in terms of the really well-studied, well-understood black holes, stellar mass black holes in the Milky Way, there's probably about 30 dynamically confirmed systems right now, roughly speaking. So very few. Binaries are really nice because they allow the objects to be studied in detail for long periods of time. Once a black hole is formed, for example, we're detecting a lot of LIGO sources. Once the black hole is formed, and it's lost from you. We can't study it continuously. On the other hand, if you have a binary system, so for example, a black hole and a normal luminous star orbiting around each other, common center of mass, then you can follow this system in detail for long periods of time by studying the emission from the companion star. However, binary evolution also changes the life cycle, the evolutionary pathway of these systems a lot. In fact, that's very important because there's many uncertainties related to binary evolution. I'm just presenting here one example of an example evolutionary pathway. This is actually for the very first LIGO detection back in 2015, I think. So we had two very massive stars, in this case, started out with 96 and 60 Sollima stars, which underwent various stages of evolution, including Roche lobe overflow, something called common envelope evolution, maybe even an X-ray binary phase where there was accretion of matter. And then finally they merged after about 10 gigayears or so to form the event that we all detected, the gravitational wave merger event. Don't worry about the individual details here. There's a lot of uncertainty. And I've listed a few, well, three of the main uncertainties here in terms of binary evolution, which we are really trying to understand. The first one is metallicity, the impact of metallicity, which means how many elements there are, heavier than hydrogen and helium in these systems, and how that impacts end-stage stellar mass loss. So massive stars give off a lot of strong winds. They are very copious emitters of winds. And it turns out that the higher the metallicity, the more is the so-called opacity to these winds, the stronger can be the mass loss. Okay? Which means that if you lose a lot of mass, then there's less mass left over to end up in the black hole. And so this is a very important uncertainty in these calculations. Another one is this common envelope phase. This is a phase where as a star evolves, the outer envelopes can expand to even encompass both components of the binary. And in this system, both systems undergo basically dissipative losses. And so you have you can get these objects spiraling inwards. And you can see here between there and there, the orbit has shrunk dramatically as a result of this common envelope phase. This is timed so almost instantaneously in gigayears, at 5 gigayears or so. This happened almost instantaneously. But we don't understand the details. We don't understand the efficiency of this process. The final uncertainty that I've listed here is magnitudes of natal kicks, natal velocity kicks. And that's what I'll be focusing on. We can't solve everything at once. I'll be trying to focus on this one issue. So what are natal kicks? Basically, these are kicks, impulse kicks that are imparted to the remnant at the instant of supernova explosion if it's formed in a supernova explosion. And conceptually, it's quite easy to understand, I think. So if you have a big boom from a supernova, big mass loss, then you expect some kind of recoil because you're losing a lot of mass. So you expect the binary system will change its period, for instance, and there'll be a perturbation, a net kick imparted to the overall center of mass. In addition to these so-called mass loss kicks, there could be, that should be natal, sorry. There could be additional natal kicks. And why should those arise? There are many reasons for that. Almost no system in nature is perfect, of course. So if you have any kind of asymmetry in the exploding supernova, for example, you can have hydrodynamic asymmetries. You can get some sort of bounce as the central compact object collapses to become a neutron star. Then some material can bounce off it, and you can have intermediate neutron stars that are formed. You can also have neutrino kicks, in this process. In fact, those can be quite important as well. You can also have gravitational wave recoil. Gravitational waves themselves carry away some linear momentum. So there's many reasons why, in addition to these mass loss kicks, you might have additional natal kicks. And we have very few observational constraints on these, especially in black holes. For pulsars have their space velocities have been studied for many years, and we think that there are several hundred kilometers per second. Their motion have been charted, so they suffer. We think they suffer quite strong kicks. Okay. And this has very important implications, for example, for the gravitational wave population. So these are some simulations showing the number of or the merger rate expected. This is as a function of redshift. Don't worry about this axis, this is not important. The main point to highlight here is if you look at this red curve, for example, this is the merger rate expected for low black hole kicks. And this green one at the bottom is for the highest black hole kicks simulated in this case. And you can see here that the stronger the kick, the fewer merger events are expected to occur. Okay, and that's simply because the stronger the kick, the binary system becomes unbound. It becomes disrupted. And so it doesn't end up as a project. So it's very important to understand these in detail. So how do we study these kicks? Well, we use astrometry, which is a fancy word, but it just means measuring very precise, well, actually, I should say positions, measuring very precise positions in the sky, which tells you information about the source distances and velocities. And the idea, it's very simple. Using astrometry is a geometric technique to constrain distances, to constrain velocities. So you're just using the perspective angle. If you want to constrain the distance to some nearby star system, you measure its angle from two different or many different perspectives in your orbit or from your satellite. You measure that angle relative to some distant reference frame, which you assume is fixed. And if you know your baseline, you measure the angle, then you can work out the distance. Very simple. So the simplest measurements, actually, in terms of distances. But these require extreme precision. That's why this has not been possible until recently. And what sort of signatures do we expect in these systems, especially for the binaries that I'm talking about? This is a schematic diagram trying to illustrate the main astrometric signatures that we expect. So you expect three signatures. You expect this parallax swing, which means every year the position of the Earth changes, and that with a 6-month period or 1 year period, basically, you expect this sort of swing. That's fixed, and you can model it quite easily. Beyond that, you can also expect some kind of linear drift, potentially, because all stars in the Milky Way, everything is in motion. Nothing is fixed, even though the sky seems fixed, but everything is drifting relative to each other. And especially if a system has undergone some kind of strong kick, and it might be undergoing very strong proper motion, for example. That's the second signature. And finally, a third one is if you have a binary system, if you can, if you have a good precision, you can actually hope to measure this wobble as the two components circle around the center of mass. You expect this wobble every single orbit. It's going to be a small perturbation, but in principle, this can be measured. And then you can get direct information on the binary system itself, on the period, on the masses of the systems. The challenges here are that you need monitoring over many, many years if you really want to build up these statistics. Many of these systems that we're studying for X-ray binaries and these compact object systems, they tend to be faint, usually, not always, but usually. Many are also transient in nature, so you have to account for variability, and they tend to be at large distances. So you need really extreme precision for this, as I said. And what really changed in the past few years, especially, is the Gaia mission, which has been phenomenal in terms of studies of the Milky Way. So it's mapping 1 billion stars in the Milky Way. That's the headline, at least. It's doing more. Goes to magnitude of 21. And it can get down to micro arcsecond astrometry for bright stars with the arcsecond painter. Okay, so milli-arcsecond is 1/1000th of an arcsecond, and an arcsecond is 1/300,000th of a degree. For those of you who don't know, it's tiny. Okay, and there's many there's progressive data releases which are happening. There's a lot of data, and a lot of the products are freely available now, so I would certainly encourage people to check it out. for your favorite sources. So what did we find? DR2, data release 2, came out in 2019, I think, or 2018. And as soon as it came out, we pounced on the data and we looked at 24 dynamically confirmed black holes, which were known at that time. And this is what we found. Okay, so you can see here all systems. So that's the position of the sun at the bottom there. All systems that we know of are mainly concentrated on the near side of the galaxy. Okay, this is not a real effect. It's just due to a bias due to obscuration, probably in the Milky Way. So there should be more systems out there, but they're faint, they're obscured through dust in the Milky Way. We just can't study them yet. And you can try to work out this astrometric distance, parallax-based distance. The median distance turns out to be about 2 kiloparsecs or so, roughly speaking. You can compare it to literature distances, and there is nice agreement overall, even though there's a lot of scatter, except for some systems there. There's a very weird one. If you want, you can ask me about it in the questions. But in general, there was good agreement, and we expect these uncertainties to decrease with future releases. So that was the distances. The real advance came, though, when we started to study their kinematics, their velocities, because now we can actually chart their motion. So these are some of the best constrained systems in which we could measure the source proper motion. We also know their third dimension of velocity, the radial velocity. So we could actually really chart out their full 3D motion in space. And then what we can compute is, we can compute the so-called peculiar velocity. Okay, there's one also up there, you can see. Peculiar velocity just means velocity over and above galactic rotation. You assume that the galaxy is like a rigid disk, essentially, which is not true, of course, but it gives you a baseline, a background. And then you subtract that out to get any excess motion. Because if you have natal kicks, you expect that to be in excess of galactic rotation. What we found was that typically you have something like 60 to 100 kilometers a second, roughly speaking, for these black hole systems, which is actually reasonably high. For reference, the sun, if you think about the reference frame of the sun, it's drifting with something like 15 kilometers a second relative to the local standard of rest.
Sure.
Yeah.
What is the clear one there?
Yeah.
There.
That one? Yeah,
Yes.
it's a
Is the one that is also clear in the other?
No,
It's
a different one.
Because
This is a runaway black hole thing. Yeah, I'll come back to it later if you want. But there's nothing very different about it compared to everything else, except it lies maybe in the halo. Yeah, very high galactic latitude, but otherwise it's quite different. It probably underwent a strong kick.
Okay.
So,
Yeah.
is it just by chance that almost all of these
So
sources?
yeah, these are the proper motions that I've depicted there. Okay, and proper motions are relative to the sun, basically. That's why. Good question, though. Well spotted. Yeah, it's difficult to illustrate otherwise without that. Okay, so you can ask yourself, what physically, what do we expect these velocities to be? If you have some kind of a natal kick, some kind of mass loss in a supernova, how do we expect these velocities to scale? You can write down this long equation. It's actually not that difficult. If you look at the different components, depends upon the companion mass, depends upon the ejected mass, on the orbital period, and on the total system mass. And even though, in detail, maybe you can't understand every single component, but in general, I hope it's clear. If you have more mass loss, then you obviously expect a stronger kick, a stronger impulse. Okay. If you have a more massive system, you expect a weaker overall perturbation. That's why you have a negative dependence there. Okay. And also, if you have a more tightly bound binary, and you have a stronger gravitational force between the components, means shorter period there, for example, and you also expect a weaker. So a relatively simple equation. And so we can now start to actually test this. Okay. And overall, you expect some kind of negative correlation between velocity and mass to 0th order. Okay, if you look at the numbers and work out how much you expect. So this is what people have been trying to test. In fact, we were not the first people to do this. This was actually by Mirabel back in 2017. Here they haven't plotted velocity. This is momentum, slightly different, but okay, about the same. Versus mass, only 5 objects or so. So very difficult to see any trend. Then with our data, we expanded the sample, got better errors, started to see some hint of correlation there between peculiar velocity and black hole mass, but still very difficult to constrain anything. Then this was an update by, I think the reference is, it's there, Atri et al. They included some radio sources as well, expanded the sample, but also induced more scatter. So again, very difficult to say what's going on. Now we've had a new data release since then. And now we have data release 3, which came out, I think, 2 years ago now. And I think this is the state of the art in terms of Gaia studies of Milky Way black holes and neutron stars as well, and binaries. So you can see here, these are all the black hole systems. These are the neutron star systems, and you can see the list if you want there. And you can work out their 3D kinematics. These are only the systems with well-constrained kinematics now. Okay. And so you can start to ask yourself, what is the best, or what is the trend we see? Oh, by the way, Roberto, that's the same object.
Poshak,
yeah.
The masses are measured by Gaia as well for these binaries, or were not?
Not from Gaia. No, they are.
So Gaia measured distances and 3D kinematics.
Yes, exactly. And the masses come from dynamical, radial velocity changes, from optical monitoring over many years, usually, for most cases.
So from the literature.
Yeah, exactly. Yeah. So what we find now is this is peculiar velocity. Again, the same quantity as before, versus, in this case, total system mass. So M1 plus M2, both components. And we actually find this is the most important quantity in terms of distinguishing. So there is a hint, well, more than a hint of a negative correlation. If you work out the statistics, it's actually quite robust. It's consistent with just simple mass loss kicks, okay? No need for any significant additional kick on average in the total sample. But of course, as you can see, there's a lot of scatter. Okay, so there's it's not a simple clean correlation. There's also clustering of different kinds of sources. So there's the SGs, super giant systems. PE are these PE X-ray binaries. So there's neutron stars, black holes. There's non-interacting systems have also been included. Pulsars are also included there. So there is a lot of heterogeneity in there. Okay? And probably we are seeing some influence of different evolutionary pathways, maybe even different kick mechanisms. And we really need to understand completeness effects in here, biases, etc. But to 0th order, if you look at the overall statistics, this is what we find. So if you just plot the histogram of kick velocities, then this is the most sort of distinguishing plane to look in. We see a difference between the high mass systems and low mass systems. The low mass systems, as you expect, they tend to undergo strong, potentially strong kicks. On the other hand, the high mass systems undergo weak kicks. By contrast, if you ask yourself, is there a difference between neutron stars and black holes? At least in our data, we don't find any obvious. So maybe they did undergo similar sorts of kicks. The kick doesn't care about the exact final compact type.
What are the critical masses of high mass and low mass?
So typically speaking, low mass are definitely less than 10 solar masses. High mass are anywhere between 10 and 40, I think is the most massive one we had. Cygnus X1 probably.
It's the total mass.
Yes, this is the total mass. Yeah.
Black hole.
Yeah. Maybe you can. Yeah. Okay. It's not really distinguished there, but you can sort of see the spread. Speak in terms of black holes. Okay. You can also ask yourself about the period dependence. So the more tightly bound binary is likely to undergo a weaker overall perturbation. And that's what we find. This is the orbital period. So basically you have tightly bound binaries are here, okay? Weakly bound binaries should be there on the right-hand side. And so any tightly bound binary can survive even a strong kick. Okay? And therefore we see that these do have stronger perturbations overall. Again, there is a significant amount of scatter overall, but they do sort of satisfy some typical constraints on binding energy. You can ask yourself, what is the typical binding energy you expect? And they all lie below the binding energy, most of them at least. Okay, so that's good. What are the implications for gravitational wave sources then from all this? Well, here, unfortunately, the situation is a bit still unclear. It's still early days. Gravitational wave sources tend to lie, of course, at the high mass end. We are detecting these gravitational wave sources, at much more massive end compared to all the electromagnetic sources that we're studying. It should be that if this scaling still applies, this negative correlation, then do they also suffer from smaller and smaller kicks? I would say it's not so clear. Just from statistical modeling of the populations, people have thought that maybe they actually do have similar kicks, like 100 kilometers a second. One important difference is that gravitational wave sources probably suffer two natal kicks, because you have two compact objects, as opposed to our X-ray binaries, we have only one compact object. So actually, by comparing these two populations, we hope that we can actually start to disentangle the effect of one kick versus another kick. So watch this space. This is still quite early. Are there any systems in which we can say with there's strong evidence of additional kicks over and above these just simple mass loss kicks? And the answer is probably yes, at least in some cases. So this plot shows the peculiar velocity relative to the expected mass loss kick in that system, okay, or the maximal mass loss kick that you expect in these systems as a function of mass. And you can see that several sources, or there's a whole bunch of objects that lie above the one-to-one correlation in here, which means that these objects, there's potential evidence that they actually had some additional kick over and above mass loss kicks. In this case, what we need to do to test this, we actually need to do proper modeling, because we are using this peculiar velocity, the current space velocity, as a proxy for the natal kick. Okay? We are saying, okay, this is how the motion is right now, and let's just say that was the kick that the system suffered when it was formed. That's not true. You actually have to do the full population synthesis modeling of these sources. Each individual system has to be modeled, and you actually have to test what sort of kicks probably that system would have undergone. And so this has now been done for several objects. This is just one example from my students' work. Here we modeled this one system, an X-ray binary. We modeled it using population synthesis modeling. So we evolved the system, forwards in time through Monte Carlo simulations, assuming different starting points, different periods, different possible periods, different possible progenitor masses, different metallicities as well, et cetera, et cetera. And that gives you a handle on potential intrinsic natal kick, this VNK. Okay? And you can see here this natal kick is several hundred kilometers a second in this case. So here we've plotted systems that didn't, or the simulations that didn't evolve into the current properties of this known system. The analogs are the ones that were successfully modeled. So these are the systems that could have ended up as the current with the current binary properties. And then you also have some disrupted systems. But in general, the natal kick is always strong in this case, or pretty much it peaks around 300 kilometers, 200 something kilometers a second, as opposed to the mass loss kick, which is only about 10 to 20 kilometers a second. So there are at least some systems that we think definitely underwent these strong kicks, but we need to do a lot more work to understand them. So I said that at the moment we only know about 30 odd black hole systems in the Milky Way, really robustly studied and understood systems. We need to expand this sample a lot more if we want to do these statistics properly. And there's many efforts ongoing to try and find more of these systems. There's imaging surveys happening, there's synoptic surveys at different wavelengths, spectroscopic searches, something called self-lensing searches as well, and astrometric wobble searches. So I'm not going to go into detail here, but basically I want to convey that people are using many different techniques to try and find black holes and neutron stars in the Milky Way, and this is a very hot topic right now. The challenge is really, there are many, many candidates, of course. The challenge is to really robustly identify the best systems. And in most cases, the best constraints come from spectroscopic radial velocity measurements, dynamical mass measurements. In terms of this astrometric wobble, I want to just touch upon this briefly. I told you already that if you have good enough statistics, you expect this astrometric wobble signature to start to stand out. And this is a very simple signature. It just depends upon, just the angular wobble is all you're looking for. So depending upon the period and the distance, you can work out what the wobble should be. And it is tiny. It's about less than a milliarc seconds for most systems. But Gaia is sensitive enough to actually try and identify such systems. And we did some work on this. So Gaia uses or reports a signature known as astrometric excess noise. So basically, they model the astrometric signature with a single star model, and then anything in any residuals that are left out could be indicators of a binary. Could be, not necessarily. So we did this, and we identified systems with this excess noise or the wobble signature. We cross-matched with Chandra. We identified about 6,500 objects. So they're plotted here. You can see there's the wobble distances. So there's a lot of systems here potentially, but they may be biased by variability, by attitude noise, and we really need to confirm all of these. Interestingly, though, we did try and compare against a control sample just to get a rough idea of the overall population statistics, and that's shown here. So in black are our candidates, X-ray binary candidates. In red are the control samples. Okay, these are basically sources without astrometric excess noise signature, but otherwise selected in exactly the same way. And we find that the candidates show many signatures of binary interaction. For example, stronger X-ray emission, more luminous X-ray emission, more frequent X-ray emission, more binaries, et cetera, et cetera. So potentially there could be some really nice systems hidden in there. But of course, following up 6,500 is challenging. We can't get enough telescope time to follow all of them, and you have to do them one by one. So watch this space. Of course, Chandra only covers a few % of the sky, and we need to expand that as well. Some of the most exciting developments, actually, in the past couple of years have come from looking at or discovering non-interacting systems. So these are objects that are not accreting. You have a quiescent, completely quiescent black hole, not even quiescent, completely non-interacting black hole or neutron star around a normal luminous star. And recently, at least even just in the past month, I think, they reported the discovery of this system, Gaia Black Hole 3, which is the most massive stellar mass black hole now reported. It's about 30 solar masses or so. So they're now starting to expand this sample of very wide orbits, very wide period binaries, which are non-interacting systems, and also massive systems there. So it's very difficult to explain their evolution. If these underwent some kind of natal kick, how did they survive? Because they have such wide period binaries, or wide periods, they should have been disrupted by now. So it's really difficult to understand that. But this is still very new. What's coming in the future? Well, in the future, we're very soon, actually, in 2027, if it stays to schedule, we should have the Roman telescope, which is the next big space mission. It's going to have it's going to be infrared optimized, and it has a field of view which is 100 times Hubble instantaneous field of view, 100 times Hubble, with similar sort of PSF, etc. And as part of that, there are many surveys being proposed. One of them is a galactic bulge time domain survey. There's others as well recently, which they're looking for. It's going to provide the deepest view of the Milky Way bulge, very high precision astrometry. So this should really, really help in terms of probing through the obscure galactic plane, finding many of these systems. And now I come to AGN. So it turns out that massive black holes can also undergo kicks, not just stellar mass black holes. Especially if you have merging systems, then they can undergo large gravitational wave recoil, because gravitational waves can also carry away a linear momentum. And then what's left over can impart a strong kick to these systems. The magnitude of these can be extremely strong, thousands of kilometers a second. Very, very strong. There's many searches ongoing for so-called dual AGN, so two different AGN together. I know some of you are working on it here much more than me, so you know more than me about this. My understanding is that all of these objects remain controversial in terms of looking for kicked black holes. There are many dual AGN candidates, dual AGN of course, but in terms of systems that have undergone a kick, we think they are very few and far between. So you expect a system to be offset from the host galaxy center of mass, for instance. It's difficult to identify these. You need good astrometry. You need other signatures. So some of the best candidates so far have been recently ruled out. But again, you probably know more than me. What I want to touch upon in the last few minutes that I have, I want to make a case, potentially, for X-ray astrometry. X-rays, I've been talking so far about optical, infrared, etc. But X-rays are arguably the best probe of an ongoing accretion activity. I think no one is going to dispute that, hopefully. Okay. The problem is that X-ray telescopes have poor angular precision, localization precision. Typical PSF, the angular diffraction limit is of the order of tens of arc seconds. The best one we have so far is about 0.5 arc seconds with Chandra. Just for comparison, Gaia that I've been talking about, best PSF is about 0.086 arc seconds. It's a small telescope in the optical, and you can get down to micro arc second precision. The reason why X-ray telescopes have this challenge is because we can't polish mirror surfaces to be diffraction limited. X-ray wavelengths are tiny, extremely tiny. At one point, the Chandra mirrors were the smoothest surfaces on Earth when they were first built. Probably still, I don't know. But yeah, it's very, very difficult to get this diffraction limit. So what can we do about this? Well, maybe we can use something else. We can use precision timing instead of spatial resolution as a proxy for good astrometry. And this has, of course, been done for a long time. This is not new. People have been doing so-called occultation studies for a long time. And what is occultation? It's basically when you have one source being eclipsed by a foreground object. If you know the exact instant of occultation, and you know the exact position of your occulting source and yourself, then you can work out, you have all the information you need to carry out precision astrometry. So precision astrometry then simply depends upon the timing, not the spatial location. Okay. What are the exact limits? How well can we do? Well, because you're working with timing, you need to optimize the count rate. Basically, the stronger is the source, the easier it is to localize, the more precisely you can localize this position. So the higher the count rate, the smaller will be the angular uncertainty, the position uncertainty. Okay, so it scales down like that. So this shows you, for example, if you have, in this case, if you have 1,000 counts per second source, then in principle, you can localize it to 10 milliarc seconds in that amount of time in a short duration. So this shows you the 5 sigma limits for this sort of experiment. The dashed curve and the dotted curve just show you different background rates. I'm happy to go into more detail there. But basically, you can get down to very interesting limits, much better than Chandra. The current best Chandra limits are shown roughly there, depending upon count rate, etc. Okay. In principle. Of course, the challenge is to get down to these really high count rates. We need to detect more and more counts from X-ray sources, and that's difficult. That means we need to scale up collecting areas hugely. Okay. And we also need a good reference frame. Because in astrometry, you need some ideal reference frame relative to which you measure it. This is all very challenging from orbit. Thank you. Yeah. So what can we do about it? Well, this is where at the end of, or no, as you advance in your career, people think you go a bit crazy, a bit loopy. So this is my moment of going maybe a bit crazy. But we are returning to the moon very soon. Okay. So this shows you just the timeline for the Artemis project, NASA's mission to return to the moon. Not going to go into details there. Look at the timelines there. It was supposed to be this year. Now it's been delayed until next year. Fine, even if it happens until the end of this decade, it's still very, very soon. NASA is being supported, of course, by ESA. So this is the ESA project to return to the moon. ESA is building a gateway. It's going to circle around the moon and enable regular landings on the moon, a lot of payload deliveries, etc. It's a big international project happening very vigorously right now. Commercial enterprises are also joining. As you know, our most loved person, Elon Musk, is going to deliver of order 100 tons of payload in principle with every flight. Okay? So there are many, many interesting options on the near horizon. So I want you to suspend your belief and imagine an X-ray telescope on the moon. What could it look like? So this is now an artist's impression, of course, of an X-ray focusing telescope on the moon. So this is the mirror, and it's just supported by a frame dome. It's an open dome. There's no winds on the moon, really, so you don't need it fully covered. It's also separate from the detectors, which sit down there. There's some solar panels there to get power, etc. So this is a focusing X-ray telescope on the moon. Because you're on the moon, you can actually build these systems to be quite large. You can get large X-ray collecting areas, potentially, hopefully. You can also build, in principle, you can allow very long focal lengths, okay? Because you don't need to connect these two. In principle, they can be separated by tens of meters, hundreds of meters. Such ideas are not new. Okay? Going back even to 1990, people have been thinking about such ideas. And this is just a very simple design of good timing detectors, actually. So no spatial resolution here, timing, good timing sensitivity, 100 square meters on the moon, which is enormous. In principle, now relatively easy to deploy in principle, if we can build it. So not only that, I think one of the most exciting prospects here is that there'll be plenty of opportunity for repeated occultations from the lunar surface. Every time a star rises above the nearby mountains and sets on the other side, it's going to undergo occultations. There's no atmosphere on the moon, almost no atmosphere on the moon. And as I said, X-ray occultations also enable looking through the obscured galactic plane. Not only that, you don't just have to rely on the topography on the mountains. You can also, since you're there, you can customize, you can build your own occulting sources. You can put your own screens wherever you want. You can deploy them, change them, whatever you want to do. You can build X-ray interferometers as well, of course, in the far future. So just to finish off with what we expect for black hole kicks. Massive black hole kicks in particular, I'm showing you, of course, for the galactic population as well, it'll be good for extragalactic systems. The kick displacements, of course, accumulate over time. So imagine a massive black hole that suffered 1,000 kilometers per second kick, and it's been drifting for 1,000 years, which is very short in cosmic terms. This is the recoil that you expect as a function of distance. On the other hand, if you have the same system drifting and accreting for 10 to the 5 years, still very short, becomes more interesting, much, much stronger recoil, starts to get almost to arc second scales. Okay. So what we need then is the question is, can we detect these systems? What are the flux limits that we can detect these to? This, for example, this is just a reference. The NICER limit, NICER is an X-ray telescope on the space station. It's built for timing studies, not big at all. It's actually quite small, but very efficient. For 10 to the minus 10 ergs per second per square centimeter, this is the limit that we can get down to. There's not many AGN known at this flux limit. We need to push it deeper. And that's where something like maybe if you have 100 times NICER, then it starts to become really interesting. Is that feasible? Maybe. NICER itself is not at all complicated. It's quite a small system, so maybe it can be deployed. Of course, I'm making it sound like it's very easy. It's not. There's many, many challenges to working from the moon. I could spend a whole hour discussing this. I'm just going to list them here. We'll have to deal with lunar dust. We'll have to deal with seismic activity. We'll have to deal with thermal changes, thermal background variations, also sky background, X-ray background, and also human activity. There'll be a lot of dust that's kicked up, for example, on sites. I can go into a lot of detail on each of these, or you can read my paper if you want. But none of these are insurmountable. There are workarounds for each one of them in principle. And since the point is that we are going to the moon anyway, if we weren't going to the moon, then I would not be proposing this. Okay, we will be there. Well, not me personally, maybe some of you young people. So it becomes a bit more interesting. But at this point, I think I've already overshot my time, so I'm going to stop. In terms of what I want you to take away from this talk is that we're learning a lot from precision astrometry, not only in terms of precision distances, but also about more fundamental formation mechanisms of these systems, compact objects. That's in particular from the natal velocities. And we're starting to find new populations of sources using these high-order astrometric statistics like wobble, etc. And there's a lot of activity on the near horizon. I couldn't even touch on some of these upcoming missions. And then maybe looking more to the future, maybe we should be more ambitious and try to exploit this opportunity. Since we are going to the moon anyway, what do we have to lose? And with that, I'll stop.
Thank you, Poshak, for this inspiring perspective. So, questions from the audience? There's already, well, okay. Let's take first a question from online. Alessandra, please.
Yes. Hi. Hey, thanks, Poshak. Yeah, it's very, very, interesting point. No, just, a comment on your vision, actually. The idea to build stuff on the moon in order to monitor the high energy sky is already, in situ, in the sense that in the plan of Earth, Moon, Mars, there's a project that is called LEMIX. It is the idea. There's the idea to put the silicon detectors on the moon. Of course, they are not telescopes. They are. Of course, it is on the way too. So they could be everything. But the idea now is to have something like concentrators. So they will not be that sensitive, but they will have a huge effective area. The ones you were talking about, 10 times nicer, it could be done. Of course, is it in the project of doing this? It's just, a project is starting an idea. However, it will be very, very interesting to develop this, discussion with you on the topic on LEMIX. So thanks for sharing
How do you spell LEMIX?
Yes, LEMIX, LEMX. I can send you something.
That'd be great. Thank you. Yeah, I wasn't aware of that.
Yeah. Thank you too.
Thanks. Yeah, I know there are some ideas on monitoring the Earth's magnetosheet from the moon, mostly in soft X-rays, but I wasn't aware of this LEMIX mission. So that's really interesting to hear.
Yeah, thanks.
Not aware of it.
So thank you for the
very interesting book. So if I understand, most of your sources, probably apart from pulsars, are binaries.
Yes, that's correct. Yeah.
So my question is, how well is theoretically known what are the conditions for your binary to be disrupted by the kick? And whether you see something, maybe an upper limit in your data, which is something you expect from higher speed than these are going to be disrupted binaries.
Yeah. So in terms of modeling of system disruption, that's basically based upon momentum conservation. You have two-body problem, and if one object suddenly loses mass, then you can work out what is the equilibrium configuration after that kick. There are codes to do this. We've also written our own. But the main uncertainties in there are some of the more basic binary evolution parameters, like this metallicity evolution, the mass loss, etc., that I mentioned before. I think in terms of just whether a kick disrupts a binary or not, I think that is fairly well or simple physics at least. But again, we don't understand the physics driving it, whether it's neutrino kicks or whether there's asymmetries in there. People are trying to model kicks in supernova simulations. So they have three-dimensional supernova hydrodynamic simulations, and they can only simulate a few, I think, milliseconds of a supernova, or maybe a bit more than that. But it's not enough to actually simulate the full kick evolution. Yeah. So the detail inside of a supernova physics is also very uncertain. Does that answer your question? Is that what you were asking?
Yeah. Well, the other part was whether the highest speeds that you get are actually an upper limit that you expect.
Right. Yeah. Yes. So far, okay. So I can show you. There's one or two systems which are a bit tantalizing and unclear. So, for example, this one on the top right. This, in principle, it lies, you can see, above this neutron star binding energy threshold there, which means that this system has too high a velocity for its orbital period. It should not have survived as a binary. It should have been disrupted. That's one system amongst many of these. So in principle, it's not a big problem. But of course, we want to understand why is this system there. There are some ideas. It turns out that when a kick happens, if the kick is oriented in a very specific direction, very fortuitous direction, then it could actually end up tightening the binary instead of disrupting it. There are so the probability of that is low. So you only expect a few such systems. There's also some supernova mechanisms where intrinsically there's no strong kick, so-called, I think, electron capture supernovae, etc. So there are some ideas, but overall they do the upper limits, I think, consistent so far.
So essentially, does this plot say that the binary systems are resistant to these kicks, that most of them resist essentially to this phenomena, right?
Yes, that's right. But of course, it's a biased sum because we are detecting the binaries that survived. All the binaries that were disrupted, we would not detect them. And that's where all the uncertainty lies in terms of completeness. We don't understand.
Because I want to ask the same question as Carl, I mean, a very similar question as Carl. So about the statistics, if there are expectations or calculations on the fraction of binary systems that are completely destroyed, in star clusters in particular, by this phenomena.
Yeah.
So the answer is that there are too many parameters.
Exactly. Yeah. I think the parameter space is huge. There are calculations, and you can set up a starting model, but it all depends upon the priors that you put into that model, on the binaries progenitor fraction, mass loss, wind loss, metallicity, common envelope phase, etc. So yeah, many things. It would be great if we can actually constrain that. Yeah, I mean, the best constraints, in some sense, maybe the best constraints might be coming from the pulsars, because pulsars are isolated systems, and we can follow them. So these might have been formed in a binary, most of them, and then ejected, and now we can study their space motion, and they tend to be quite high in general. that gives some constraint.
Questions?
You must sound really stupid, but
That's
what
okay.
chances that you're having the ternary systems for those outliers
With a lot of difficulty. Yeah, good question. So what's the chance of ternary systems? So I would say for these objects, they have been studied in a fair bit of detail. So we have radial velocity measurements, and we've modeled, I think people have modeled their orbits quite well. So there's not expected to be many ternary systems in here. But when people have been searching for new systems, recently in these searches for non-interacting binaries, there were many candidates that were reported over the past 2-3 years. And interestingly, several of them turned out to be ternary systems or some kind of weird binary stripped envelope systems, etc., which haven't really been found before. So they definitely exist. Some of them exist, yeah. But as to the fraction of them, it's unclear how many.
Is there any statistics of what is the ratio between ternary to binary systems? So what would we expect to see, right? Based on modeling?
Yeah, I'm not aware. I mean, there probably is, but I'm personally not aware. Again, depends upon what mass function you set up and binary, ternary, multiplicity fraction you set up. Yeah, maybe studies of star clusters, ignoring compact objects, just looking at the fraction of multiplicity in star clusters will help you there.
Other questions? If not, I will reserve my question for the
Yes.
afternoon.
Okay, fine.
Thanks again, Poshak. Once again, if you have curiosities, I think you'll be happy to answer
Oh yeah,
all of them.
absolutely.
Or, yeah, that's all. Third floor guest office.
Yeah.
Thank you.
Thanks.
So il prossimo evento deve access all these sources guy we channel because but because it's obvious catalog, no hope with the XMN one.
PSF.
Because the PSF is terrible.
The galactic plane, it becomes
So the
difficult.
PSF is terrible.
The same in Rosita. Down.
I was thinking.
Yes, of course.
If I imagine that everything on the bottom, what the back is on, having a test on the moon technology.
Yeah, so the main advantage is just engineering. It becomes much easier.